So welcome back everyone to this Young Researchers in Spectral Geometry conference. And for the second talk of the day, we have the pleasure of having Laura Monk from IRMA Strasbourg. And she will speak about geometry and spectrum of typical hyperbolic surfaces. The floor is yours.
Okay, thank you very much, and thank you for the invitation. So today I'm going to try and present things about the geometry and the spectrum of typical hyperbolic surfaces, and I'm going to mostly emphasize on the links between geometry and spectrum, and what kind of geometric information we need to acquire spectral information. So I don't. Okay, so the setting in which I will be is the setting of compact hyperbolic surfaces. So I will consider a surface X, which is topologically like this. So it's the only thing you need to know to understand its topology is the genus G, which is a number greater than 2. So there's no cusps, the surface is connected and everything, it's just, and no boundary, it's just something like this. And I will put a constant curvature -1, so it's going to be a hyperbolic surface, which means that locally it's isometric to the hyperbolic plane H, which can be seen as the complex upper plane with this usual metric. The Gauss-Bonnet formula implies that the area of such a surface is 2 pi times 2g minus 2, so roughly proportionate to the genus. So I will place myself in the asymptotic g going to infinity, which will correspond both to having more and more topology, so more and more holes in my surface, but also having a surface of area going to infinity, so a large scale limit. So I'm having problems passing the slides. What's happening? I'm sorry about that. Okay. So the outline of the talk is as follows. First, I'm going to say what we can say of the spectrum of any surface like this, and compare it to what we can say of the spectrum of most of these surfaces. Then I'll explain how the Selberg trace formula allows us to study the spectrum by understanding the geometry, and how understanding the spectrum is related to understanding long geodesics. And it might be a bit technical at some point, so if you get a bit lost, it's okay, brace yourself, because the third part is going to be a geometric part, which has nothing to do with the second, and wonders about how does a typical surface look like geometrically with drawings and things. So the question I'm going to try and answer today is, what can we say of the spectrum of the Laplacian on a compact surface? So first, simple observation is that 0 is always a simple eigenvalue corresponding to the constant eigenfunctions. And there's another number which is quite special, which is a quarter. And the reason for that is that the hyperbolic plane, which is not compact, so doesn't have a discrete spectrum, actually has a continuous spectrum, which is a quarter plus infinity. So a quarter is going to play a very special role in this talk. And eigenvalues under a quarter are a bit special, and they're called small eigenvalues. They appear in many things on very different, in very different fields. So, for instance, they appear in the Selberg conjecture, which is a conjecture in number theory, which says that for a certain class of surfaces which come from number theory, which are congruent surfaces, there's no small eigenvalues. Another place in which they appear is in the prime number theorem. So it seems a bit, so it's not really linked to prime numbers. So the prime number theorem is, the question is, if I set a fixed number L and I want to count all the closed geodesics which have a length shorter than this number L, then what is the behavior of this quantity as L goes to infinity? So it's a bit like the question of what is the behavior of the number of prime numbers up to a certain size. So that's why it's called like this. And whether or not a surface has small eigenvalues is going to influence this asymptotic behavior. It is also linked to the mixing time of the Brownian motion, so to dynamical properties on the surface. So small eigenvalues appear really in very different fields of mathematics. My aim is going to be to provide information on the number n of AB, which is the number of eigenvalues between A and B. So first, I'm going to look at the bottom of the spectrum, that is to say small eigenvalues. And the first observation we can see, which has been proved actually quite recently, is that the number of small eigenvalues is smaller than 2g minus 2. So it can be bounded by something linear in the genus. And this bound is actually optimal. And not only is it optimal, but so not only is this bound optimal, but if you replace 1/4 by any smaller number, there is a surface which has 2g minus 2 eigenvalues between 0 and epsilon, for epsilon arbitrarily large. So a hyperbolic surface can have up to 2g minus 2 small eigenvalues, and they can also all be very close to 0. The proof of this fact can be obtained by using the min-max principle and what we call the pinching argument. So you take a genus G surface, like I represented here for a genus G equal 2, and you cut it in pairs of points. So a pair of points is a surface which has 3 boundary components, like a pair of pantos, the belt and the 2 ankles. So here you see that this surface, I cut it using these 3 curves into 2, which is 2 times 2 minus 2 pairs of points. And then what I can do is I can pinch the curves I cut here. And a very important fact in hyperbolic geometry is that if you pinch a curve, locally around the curve, the surface looks like a cylinder. And when you pinch the curve, the cylinder becomes very wide. That comes from the hyperbolic geometry. And therefore, if you pinch the surface, you obtain a surface which has very narrow cylinders here, which are kind of bottlenecks, and separate those 2 pairs of points. So then you can construct some functions which are, each function is supported in one of the pair of points. It's one very like inside the pair of points, and it goes slowly from 1 to 0, and it's 0 starting here and 0 on the other pair of points. And on each function you can define, on each pair of points you can define a function like this. And this is going to give you a family of orthogonal functions. And the Rayleigh quotients are going to be small because the function is almost constant, except from this very long cylinder on which it goes very slowly, and the cylinder is small. So these Rayleigh quotients are all going to be small and be made arbitrarily small, actually. So by the min-max principle, you obtain that there can be up to as many small eigenvalues as there are functions here. So 2g minus 2. The reason why this example is interesting is that it shows a case where we have an inequality and it's made optimal by finding examples, but the examples we construct are really pathological. We really try to make the surface break. We pinched curves. It's some kind of limit surfaces where something bad happens. And the aim of my research project is to say that these surfaces are somehow pathological, and that we don't have, we can prove results which are true most of the time, and which are better than what these surfaces satisfy. So above 1/4, the situation is quite different. So a first observation is that due to the fact that the spectrum of the hyperbolic plane starts at 1/4, you can prove that lambda1 is always going to be smaller than 1/4 plus something that goes to 0 as the genus G goes to infinity. So the large genus limit corresponds to surfaces which become bigger and bigger, and they're going to become, in a sense, possibly close to the hyperbolic plane, and the hyperbolic plane has spectrum starting at 1/4. So therefore, when they become big, they're going to have spectrum starting at 1/4. So there's always an eigenvalue a bit above 1/4 in our limits. Furthermore, you cannot prove a topological bound on the number of eigenvalues above 1/4. So here, in the first case, the number of eigenvalues under 1/4 was bound by something which only depends on the genus. And that's no longer possible if you want to go a bit above 1/4. There are surfaces of fixed genus with an arbitrarily large number of eigenvalues between 0 and 1/4 plus epsilon, if epsilon is strictly positive. So there can be many eigenvalues just above 1/4, and that's also somehow topological. You wouldn't expect surfaces to suddenly have so many eigenvalues above 1/4. So first result I want to present is the fact that for typical surfaces, so that I'm going to explain a tiny bit more later, but I don't want to put the emphasis on this too much right now. So typical surfaces means most surfaces for a certain probabilistic model, which I'll introduce quickly later. But so just now you need to think it's most surfaces. So for most surfaces of high genus, the number of eigenvalues between 0 and b divided by the area of the surface can be bounded by something like this. So let's take a few values of b to see what happens in this bound. If we take b equals to 1/4, we obtain that the number of small eigenvalues is big O of g divided by a power of log g. So this is a logarithmic correction compared to the deterministic bound, which was optimal. So these examples, the surfaces which are obtained by pinching all these curves, they're not typical. They're quite pathological and exceptional in a sense. And most surfaces actually satisfy a bit better, a bound which is a bit smaller. And actually, if now you take b to be smaller than 1/4, to be a small epsilon, you obtain a power of g. So not only do you have this logarithmic correction, but you actually obtain a negative power of the genus. So the bound becomes better if you want to study eigenvalues between 0 and epsilon rather than 0 and 1/4. So these examples where the 2g minus 2 eigenvalues are all really close to 0 are also even more pathological. Furthermore, if you take b to be greater than 1/4, for instance 1/4 plus epsilon, or even an arbitrarily large value, you obtain a bound which only depends on the topology of the surface. So this, the fact that you cannot bound the number of eigenvalues by something only depending on the genus becomes false. So, however, it is a really pretty bad bound. If you take b to be a very large number here, it's g to the power a very large number. It's a bad bound. However, it's a bound which only depends on the topology, which is different to what we observe if we consider any surface. A next step is to not only understand how many small eigenvalues there is, but where is the smallest one of them, the smallest non-trivial eigenvalue, lambda1. The first step for this, so the first observation is that due to the optimality in the first statement here, lambda1 can be arbitrarily close to 0. However, the first step towards proving that this is not typical was achieved by Mirzakhani using Cheeger inequality. And she proved that lambda1 can be bounded by something which is a constant. well, something very small, but still something which is a constant. So that's still going to be true only for typical surfaces, most of the surfaces. The next step was achieved very recently, a month ago, by two in different teams, one in China and the other in the US. And they proved that lambda1 is greater than 3 out of 16 minus epsilon for epsilon arbitrarily small. So this is a significant jump in quality of the estimates. And such estimates are actually, the same exact estimate has actually been proven for different models of typical surfaces. So there's another model using random covers in which the same result has been proven last year. I'm currently working with my advisor, Nalini and Theorem, on proving the result with a quarter rather than 3 out of 16. This would be the optimal result because we know that lambda1 is bounded by a quarter plus something going to 0. So you couldn't replace a quarter by any bigger value here. So there's two kinds of spectral geometries. There's some who are interested in the bottom of the spectrum and some who are interested in high energies. You can also say things about high energies for typical surfaces. So the most common statement for high energy is the Weyl law. In the setting of compact hyperbolic surfaces, the best result we have says that the number of eigenvalues between 0 and b, where b is a large number going to infinity, divided by the area of the surface is b divided by 4 pi, plus a constant plus something which is negligible, but there is an implied constant here which depends on the surface and the geometry of the surface. One of the results I'm going to talk about states that for typical surfaces, you can actually do a lot more precise and say that the number of eigenvalues between A and B, where A and B are two numbers greater than a quarter, which are not too close, so you can't take too small a window. This number of eigenvalues divided by the area of the surface is actually equivalent to a certain quantity, which corresponds to the spectral density of the hyperbolic plane. So let's represent this. I have my a plot representing the density of the spectrum divided by the area. And the density of the hyperbolic plane is a function which starts at a quarter, goes up very, very quickly, and then has a plateau at 1 divided by 4 pi. And what this statement says is that the number of eigenvalues between A and B is well approximated by the area under this curve. So in particular, below a quarter, you don't expect there to be a lot of eigenvalues. And starting at a quarter, the number of eigenvalues is going to be, well, quite quickly, approximately b minus a divided by 4 pi. And actually, if you take a equal to 0 and b going to infinity, since this area under this curve is going to go quite quickly, to be quite quickly similar to b divided by 4 pi, you recover a uniform Weyl law, which with a constant here, which does not depend on the surface, which is great because we can construct surfaces with a bad constant actually. So the picture, if you want to imagine the spectrum of most surfaces, is like I represented. There is a spectral gap, which goes at least until 3 out of 16, and hopefully we believe up until a quarter. And then there starts to be some spectrum, and the spectrum has the histogram of the spectrum is this curve in the limit g going to infinity. So that gives quite a detailed picture on the spectrum of a typical surface, which we cannot achieve for any surface. So in order to explain how we can prove these sort of statements, I'm going to introduce you to the Selberg trace formula and to different methods to prove these results. So in order to state the Selberg trace formula, for each integer j, we're going to pick a complex number r, such that the lambda, the eigenvalue, is a quarter plus r squared. This change of variable is necessary. It makes everything behave more nicely. So the thing is, if lambda is greater than a quarter, then r is a real number. However, when lambda is smaller than a quarter, this r is actually a complex number, which is on the imaginary axis between minus I/2 and I/2. And actually, the eigenvalue 0, the trivial eigenvalue, is one of these two values, I/2 or minus I/2. And this is one way in which the small eigenvalues are going to act in a special way. In order to write the trace formula, you need to pick a test function, which is going to be called h. And we will say it's admissible if it satisfies the full properties, which are quite nice. I mean, not anything too dramatic. It needs to be even, so that your choice of Rj doesn't matter too much. So just even. It needs to be analytic in a strip containing all the possible R's. And it needs to have a nice north decay. So here, a polynomial decay, for instance, a bit better than 1 over r squared. So when you go to the edges of the strip, it needs to decay fast enough. So that's nothing too dramatic. And we're going to be interested in the inverse Fourier transform of h, which I will denote like this. And the Selberg trace formula can be stated as this expression. So big formula, I'm going to walk you through all the terms one after the other only. The first term here is a spectral term. Everything here is going to be very different depending on the test function you consider. So I'm going to take an example of a test function, which is the one I use in my proof actually. So for instance, if you want to count the eigenvalues between two values a and b, you can write a and b as a quarter plus alpha squared and a quarter plus beta squared. And then you can pick the test function h to be a smooth approximation of the indicator function. So here you have to be careful. You can't take the indicator function because you need your test function to be smooth. So you have to take a smooth version of it. And then in this case, you're going to sum over j the indicator function of Rj. So when Rj is between alpha and beta, it's going to be 1 and otherwise 0. That is to say, the spectral term would be approximately the number of eigenvalues between A and B. So this term is going to give you exactly what you want. However, the error term, the difference between this and the counting function, is going to be depending on how close h is to the indicator function. And it's going to get better and better if you take h to be more and more irregular. So you're going to want to push h as close as you can to the step function. The next term is called the topological term for the simple reason that it doesn't really depend on the surface. Here you have an integral with the test function, and the only place where the surface intervenes is here, but the area of the surface is just depending on G, on the topology. For this test function, the one we picked so far, this term is going to be about approximately this. And this is precisely the spectral density of the Laplacian. So you understand how this quantity of the result is really natural thing. It's the thing that appears in this term of the trace formula. And in a sense, it's kind of comparing your surface to the hyperbolic plane. However, and this is where you get in trouble, there is this geometric term, which is quite difficult to deal with and can vary a lot between surfaces. So the geometric term is a sum over all closed geodesics of a certain function which only depends on the closed geodesic times the inverse Fourier transform of h applied to the length of gamma. So that's very interesting, because then this formula, what it says is that if I sample all the spectrum using H, it's linked to sampling all the lengths of all the closed geodesic using the Fourier transform of H. So it's really a fun game to play between these two quantities. It's interesting relation between the two. So here, if we take my friend the function H, and I take the Fourier transform, I'm going to get something which looks a bit like this. For instance, it kind of depends on how you construct H, but mostly you can make it so that there's an exponential decay. And the thing is, as you know, when a function is very smooth, its Fourier transform decays very well. So when it's not smooth, its Fourier transform decays less well, and it spreads. So if I want to take H, which gets closer to the indicator function, the size of this envelope, the typical width of the support of H hat is going to spread. So that's going to be a limiting factor. In order to have precise estimates on the first two terms, I need to make H irregular. And this is going to cause H hats to spread. And therefore, if I represent by these little crosses the lengths of the eigenvalue of the closed geodesics, so these arguments here, more and more of them are going to contribute to the sum. So not only, so one thing is, if there are some small geodesics, they will be there, can't do anything about them. And also, the more precise you want to get, the longer and longer geodesics you're going to need to understand. So yes. And this kind of corresponds to the fact that earlier we saw examples in which there was a lot of small geodesics and in which this term actually was really big. Now I'm going, so this is the way to prove the result about the density. Now I'm going to explain a bit how you can try to prove things about the spectral gap using the trace formula. So in order to make the discussion simpler, I'm going to assume that you take a test function which is positive, of positive Fourier transform, sorry for the reverse hat, and such that the support of the Fourier transform is included in a compact, is compact, so it's minus LL. As I said, in order to have a precise thing, we expect the support to spread, so L is going to be large. I'm going to have a look at this term and single out the first two terms corresponding to the trivial eigenvalue and then the first non-trivial eigenvalue. So the first, the trivial eigenvalue corresponds to, so it's lambda 0 equals 0. So it corresponds to R0 equals, for instance, minus I over 2. I can write H using the inverse Fourier transform as the Fourier transform of H hat. And I obtain here something with an exponential of I R naught psi. And if I replace R naught with my complex number here, I obtain exponential of psi over 2, which is a positive exponential, which is quite big. And here, the Fourier transform is positive. So I'm integrating a positive function against an exponential. This is going to be a bit smaller, actually, but roughly, for the sake of simplicity, let's say this is going to be roughly exponential of L over 2. So it's going to be, recall that L is a big number, it's going to behave exponentially in L. By the same argument, if lambda 1 is a small eigenvalue, you can write it as a quarter minus alpha squared, and then the second term is going to be exponential of alpha L. So you have a leading term exponential of L over 2, and the second term exponential of alpha L. So it's a bit like when you do trace arguments for graphs. You have arguments which are smaller and smaller depending on the size of the eigenvalue. And then the rest here is a positive quantity. So what you can observe is that if you can prove that this part of the sum, so the sum starting at 1, you forget about the leading term, you remove it because it's hiding away what's happening. So you remove the leading term, and if you can prove that the rest of the sum is a lot smaller than exponential of alpha L, then it means that you can't have this contribution. And hence it means that lambda 1 has to be at least a quarter minus alpha squared. So it gives you a lower bound on lambda 1. So you need to understand, you need to prove a bound on this quantity. In order to do so, you look at the right-hand side of the formula. You want to prove that this right-hand side is not behaving exponentially in L. The first term is the topological term. So you want to prove that this topological term is not exponential in L. And actually, we know it's linear in the genus G because of the fact that the area is linear in G. And we are taking G going to infinity. So this is going to force us to take L to be A log of G, and actually A to be quite a large number possibly. So this forces us to look at length A log G. I recall that the support of H hat is minus LL, and here there's H hat. So the support of H hat is going to tell us which sizes of geodesics we need to look in this term. And in order for this term to not be too big and not blur out everything, we're going to take very long lengths, length L equal to A log G. And actually in the two papers, in the two very recent papers which prove that lambda 1 is greater than 3 out of 16 minus epsilon, they take A equal 4. But you can see very naturally that in order to get to a quarter, you need to take A arbitrarily large, and that's quite challenging, as we will see in the second part of the talk. Then the last term to study is the geometric term, and that's where everything is. That's the whole complexity of the thing. It's really challenging. It depends on the model you're using, and it requires you to understand all the geodesics up to a length L, and to do a very detailed study. In both those recent articles, there's actually something quite magical which they observed, which is that the leading term on the left-hand side, so H of R naught, is actually precisely cancelling the leading term of this sum, so the expectation with regards to their probabilistic model of the geometric term, but where you restrict the sum to simple primitive geodesics, so geodesics which don't have any self-intersection and which are which you go along only once. So they actually managed to find a precise term here, to counterbalance the leading term here by a very concrete and explicit term here. In order, so then you only need to prove that the rest of this sum, where you remove the simple primitive geodesics, is small. This is actually what's difficult. The only is really not an only, because this is really difficult. It's the most difficult part of the proof, and they do it in two very different ways. With Nalini and Theorem, we use a very different method to exhibit cancellations, which has the benefit of possibly being able to go to a quarter, because this approximation is not going to be good enough to go to a quarter. It breaks down at 3 out of 16 once again. Okay, so here's done for the spectral theory part. It got a bit technical, perhaps, but we are going to talk about geometry now. So if you are a bit lost, it's time to catch up. In order to study typical surfaces, there's different probabilistic models. It's not really straightforward to know how to take random surfaces. There's one quite combinatorial model by Brooks and McCover in 2004. There's one which is more algebraic and based on coverings, which gave good results last year. But the one I'm going to talk about, and the one that I used in all the previous results, is the model by Mirzakhani, which she developed in 2013, and it's called the Weil-Petersen model. And what's great about this is that it's really natural and very geometric at the same time. So the basic idea is that you take the moduli space, MG, which is the set of all hyperbolic surfaces of genus G, so the set you want to work on, and you quotient it by isometry. You identify the surfaces which are isometric to one another. So that's exactly the set you want to study if you want to take a typical hyperbolic surface of genus G. And you can prove that it is equipped with a finite volume form, which is actually induced by a symplectic structure, but that's not very important for us, but it's actually very powerful. And since it's a finite volume, you can normalize it by dividing by the total mass, and you obtain a probability measure on the set Mg of hyperbolic surfaces of genus G, which is a very reasonable way to define a random surface. We take the set of surfaces, you put a probability measure on it. And it's really nice because this volume, which we started with, is actually the Lebesgue measure in a set of coordinates, which is called the Fenton-Nielsen coordinates. So I take my genus 2 surface once again, and if I cut it in pairs of points, so I cut a few curves here so that the result once cutting is some pairs of points, you can prove that the geometry on the surface is entirely determined by knowing the lengths of all these curves. So L1, L2, and L3 are the lengths of all these curves, plus some twist angle, which is which correspond to, because when you glue together two pairs of points, you have a degree of freedom. You can glue them together straight away, or you can turn a bit one of them and then glue them. And this is precisely the twist angle. And if you can prove that if you know all these lengths and all these angles, then you understand entirely the surface. So that's a set of coordinates on the set of surfaces. And in this coordinate system, our volume is the Lebesgue measure. So it's a very natural way to sample random surfaces and corresponds to a geometric thing on the surface too. And thanks to Mirzakhani's work, it's actually possible to do things with this system and to compute the probability of events. It's not only an abstract tool. So the events I'm going to talk about are events true with high probability. So their probability is going to 1 as the genus G goes to infinity. It's not almost sure, therefore, it's weaker than almost surely. They become more and more likely when the genus G goes to infinity. And we know that we want to understand small geodesics. So the first question to ask is, what is the length of the systole? The systole is the shortest closed geodesic. What can we tell about its length? We are imagining surfaces which become big and bigger. So we can maybe hope that perhaps the systole is becoming big. And unfortunately, it is not the case. Mirzakhani proved with Petri that the fact of having a closed geodesic of length smaller than epsilon, where epsilon is a fixed positive number, is actually going to look like a Poisson law with an explicit parameter. So Poisson law are the kind of probabilistic laws which you take to study events which are unlikely but kind of happen. They are rare. So having a very short geodesic is something that is bound to happen. It's not going to happen all the time. It might happen a bit. Many times that's unlikely. It's a rare event. For instance, as a consequence from that, if you take epsilon to be very, very small, you can prove that the probability of the systole being smaller than epsilon is roughly epsilon squared over 4. So if epsilon is a very small fixed number, it is not true that with high probability, with probability going to 1, the surface won't have curves smaller than epsilon. It is possible it will have very small curves. And that's non-convenient. We don't want the surface to have very small closed geodesics, but it might be the case. And actually, you can also prove that the expectation of the length of the systole is this finite number, which is not even that big, So really, the length of the systole is quite a fairly small number. If I draw my surface, the smallest closed geodesic is not going to be super big. So the aim of my work is to find other ways to say that there's not too many closed geodesics. There are some, okay, that's life, but I want to say that there's not too many. And the first way to say that is to talk about Benjamini-Schramm convergence, which is a notion which was adopted from graph theory. So we can prove that with high probability, if you take a point Z on the surface, so now you fix your surface. You have a surface which is typical. And you take a point Z at random. You throw it on your surface at random. Then you can prove that for most of these points, for most of these Zs, there is a very large neighborhood of Z, which is a ball. There is the ball of radius, a 6 of log G, is actually a ball. So meaning that if you, the fact of taking a point Z, which is in this bad area, so if you take a point Z in this area and you try to make a big ball around that, it's going to self-intersect and it's not really going to be a ball. So these set of points, which are the bad points, which belong to a thin part of the surface where the injectivity radius is small, is negligible compared to the volume of the whole surface. So the volume of all these orange parts is negligible compared to the volume of the whole surface. There is a very little proportion of the surface which is thin. And this notion is enough to prove the bound on the number of small eigenvalues and the spectral density result, as is the case in graphs, actually. But this is only an estimate about the volume of this set of points. So it just says that the thin part of the surface doesn't make up a big part of the surface. The next step is to wonder, how are the small geodesics distributed on the surface? Can there be small clusters? So here I represented two surfaces of the same large genus. And in one case, the small geodesics are here and there, distributed in very different parts of the surface. And in the other case, they're all together in a part of the surface which is quite thin. And the question is, what's more typical, one or the other, or neither? Due to similarities with graph theories, we were expecting that the surface on the left was more typical than the surface on the right. But we needed to find a way to express this. And the way to do that is to notice that if there's a lot of small geodesics close to each other, then there is a small pair of points. Here you can see two of them, which have a very short boundary. So I proved with Joe Thomas that with high probability, random surfaces have no embedded pairs of points. So pairs of points are like this. Or handles. So handles are like the handle of a mug. There's one boundary component and there's genus 1. And there are no embedded pairs of points or handles of total boundary length smaller than 2a log g, where a is a number smaller than 1. So we call this property being tangle-free due to similarity with graph theory, where the same notion is used in spectral theory. And one intuition for that is that if you have a small pair of points or a small handle, you can draw an 8 on the pair of points or on the handle. And it's a tangled geodesic. So having a small pair of points or handle is linked to having a small tangled geodesics. You can prove that any genus G surface is 4 log G tangled. So in this sense, random surfaces are almost optimally tangle-free up to a constant. And this notion is actually the probabilistic assumption they use in one, but not both of the approaches to prove the spectral gap, 3 out of 16 minus epsilon. The tangle-free assumption has consequences. So you can prove using this notion that closed geodesics of length smaller than a log G are simple. So as I showed here, there's non-simple small geodesics in pairs of quantum handles, and actually you can prove that if you don't have pairs of quantum handles, you don't have non-simple closed geodesics. So all these little closed geodesics are simple. And also you can prove that if the sum of the length of two closed geodesics is not too big, then these two geodesics do not intersect. And you can actually prove that they are far away from one another, bound the distance between them. So so if I wanted to draw all the closed geodesics on my surface, the picture would look like this. Furthermore, you can improve a lemma, which is very, very, very used in hyperbolic geometry, which is called the Kohler lemma. So topologically, you know that if you have I actually used it before at the beginning of the talk. So you know that if you have a short, simple curve, there's a neighborhood topologically of the curve, which is a cylinder. And what's great with the Kohler lemma is it gives you an explicit width of this cylinder, which depends on the length of the curve. And the problem is with the longer the geodesic is, the shortest the cylinder is. And thanks to the tangle-free hypothesis, you can actually make this a lot better. You can find an embedded cylinder of width a log g minus L over 2, which if L is b log g, with b small, like, let's say if L is a over 2 log g, this is going to be logarithmic. It's going to be a very, very big cylinder. So here, thank you for your attention, and I'm open to any questions you might have.
Thank you very much for this nice talk. And we have time for any questions. If people have questions, please just unmute yourself and ask your questions.
May I ask a question? It's Yves Collet de Verdière. You hear me?
Hi. Yes, Yves, I can hear you.
Okay. My question is, how far are you to prove your conjecture with Nalini?
We have a very detailed plan. And we know that it works, that the first terms work, but we are struggling with the complicated geodesics. So there still needs maybe 6 months, a year, I think. Yeah, but it's going okay. There. Well, okay. Maybe more. I don't want to put a bet on it, but we're going in this direction. We have a very detailed.
You have already so many results. It's very nice. Thank you.
Anyone else wants to ask a question?
Ask a question quickly?
Yes, sure.
It was a wonderful talk. Thank you very much, Laura.
Thank you.
I guess one question I had was because I'm not very familiar with this sort of Weil-Petersen model. I'm sort of curious if sort of knowing any results about the say sort of geometry of Weil-Petersen, or moduli space with this metric could give you sort of improved probabilistic results, because I know that there's sort of some work also about the spectral geometry of moduli space itself, right? The Laplacian has an essentially self-adjoint extension with respect to this metric. So I guess I'm just curious if this is if you or Nalini have thought about this at all.
It's interesting because, for instance, for some of the geometric events, you can understand really where it goes bad. So, for instance, it goes bad towards the boundary of the moduli space. And what happens really is that you measure the size of this boundary and you cut things. And there's actually there's a very nice article by Mundal where he shows, for instance, he studies the topology on the set of surfaces such that lambda1 is greater than a quarter on the moduli space of surfaces of genus 2. And he proves that a lot of, on M2, so on the set of surfaces of genus 2, there's a lot of surfaces which have a spectral gap a quarter. And he does that by really studying the topology of this set of surfaces. So there's interesting questions like this. It's another way to quantify how many is to understand where they are on this set. So the understanding of the geometry can be useful to that, indeed.
Could I just ask again, who was the other author you mentioned?
Mondal, M-O-N-D-A-L.
Thank you.
So you mentioned that in some cases the bad geometric events are close to the boundary of this moduli space. Are there some bad geometric events that also happen inside, or they're all on boundary?
I actually don't know where the non-tangle freeness happens. That's a good question. I do not know that. The fact of having a short injectivity radius is going to the boundary, but
Thanks.
I have a naive question. You said that in the coordinate, coordinate, the measure is the Lebesgue measure. So do you have to use the symplectic structure, or you work with this Lebesgue measure in coordinate?
So it's very deep actually. There's a lot of you could believe that there's a lot of choices here. When you it's actually later. When you cut your surface in Benjamin's coordinate, you have to pick a pair of decomposition and initial angles for the twists, and there's a lot of choices. And it's really thanks to the symplectic structure that you're able to understand that this volume form doesn't really depend on any choices you've made. And you really deeply need that. And the integration formula also requires that you have a lot of structure, of underlying structure. It wouldn't be enough to just know that in one way of cutting the surface, it's the Lebesgue measure. That would be very insufficient.
Thank you.
But then why is this measure finite volume? Because
it's finite volume because you can construct, you can show that using the Bayes constant that any hyperbolic surface can be cut in pairs of points with lengths which are controlled by a number, the Bayes constant.
Okay.
And then the twist angles can be between 0 and L on everything. And there's a finite number of ways to cut the surface into pairs of points. So at the end of the day...
So you need to have a covering with different charts of your moduli space?
Exactly. You obtain not really a fundamental domain because it's going to overlap, but you obtain a finite number of things by which you cover, and every one of them has a finite volume.
Okay.
You can also see that because there's a natural compactification of the moduli space, and therefore it's going to be of finite volume in the compactification. But that's a bit more.
Okay, I see.
So I have one last very naive question. The different random models that are there, the Bailey surface random covering, how are they related to one another?
It's interesting because they all seem to have similar properties in ways, but not exactly the same. You have different rules in every case. And for instance, I think if I remember, well, in the first two models, the systole is not going to be very small, as opposed to the last model. But however, I actually proved recently it's not very difficult that the random covering Benjamin Schramm converge, so the spectral density is going to converge too. I don't expect it to be true in the first case. So there's different situations here. And I think you can just pick your weapon depending on what you try to do. But in all these cases, there's still, I mean, we still always have a spectral gap. That's nice. And we still have ideas of like having not too many closed geodesics and things like that. So
is one of this model similar to choosing random graphs and building surfaces from these graphs?
Yes, the random Bailey surfaces consist in taking some triangles, a finite number of them, and picking any kind of way to glue these triangles together. So it's very combinatorial. And what's great is that Bailey showed that you obtain a dense subset of the set of surfaces this way. So you obtain only a discrete number of surfaces, but it's kind of dense, so you have something representative in a sense.
Thank you. Anyone else wants to ask a question or comment on something? If not, let's thank Laura again. Thank you for this very nice talk.
Thank you.